Hello everyone, this is the lecture I promised that is going to replace our lecture on March 31st. If you recall, that lecture lost its audio midway, so I'm going to redo the lecture. It is going to be a little shorter than 1 hour and 15 minutes, mainly because we are not in a class setting, and at the beginning of the lecture we had this attendance quiz. If you haven't submitted your attendance quiz, this was the attendance quiz. If this is your first time watching this lecture, make sure to submit this to get the grade. Attendance quiz was, what is the difference between flow over wings and flow over infinite wings? So in one case your B is, or a span is a finite number, and in another case your span is an infinite number. This lecture is going to mainly focus on, and please go ahead and submit this if this is the first time you're watching this and you haven't submitted your attendance quiz. In this lecture we are going to mainly focus on the type of wings, how they are located on a plane, and different designs and fluid flow over air or airflow over those different designs. So the first thing we need to talk about is the type of wings. We are mainly focused on 4 different types of wings. First is called a rectangular wing. And you just have to keep in mind that these are all top views of the wing. So a side view of a rectangular wing will look something like this. It will have an airfoil, then a span, same airfoil, same chord length. It looks like something like that, and you will have the fuselage in the middle, and this is going to be your plane. So these are top views. Okay. We're looking at this from this top angle, and it is possible for us, and this is, let me name all of these. This is the midplane of the wing, quarter chord line, C/4. This is going to be the leading edge line, and this is the trailing edge line, and this picture is going to be the leading edge here, trailing edge here. It is possible for us to have a wing that doesn't have the same chord length throughout. If you look at this wing, the chord length of the airfoil of that cross section of the wing is uniform. So we can have a wing with a non-uniform chord. This is going to be your midplane or roots, and the chord plane of the root is called CR. This is going to be the chord length of the tip. So root of the wing, tip of the wing, and we use CT to identify them. You also have to keep in mind the span of the wing is usually B in our cases. There are a couple of examples that we don't really use B, but we use 2S for the span of the wing. So if you somehow saw 2S for the span, don't be confused. And these type of wings are called unswept trapezoidal wings, or called the tapered wings. It is also possible for the wing to have something called a sweep angle. I'm pretty sure you have seen these type of wings, especially on military type aircrafts. You have the mid-plane or the root, again here, root of the wing, CR, CT. They can be different in this case, or they can be the same, doesn't matter. The thing that we are focused on, the part that we are focused on here, is this angle, lambda. This is the angle that your chord line makes with the horizontal line here. And it's called lambda of C/4. We can have the same angle for the leading edge, lambda of the leading edge. We can also have the same angle for the trailing edge. These type of wings are called swept wings. We'll talk about their applications and everything else later on. There is one more type of wing that we need to focus on, and it's called the delta wing. Delta wings are a special form of swept wings. Their root chord is this, but their tip chord is 0. So the quarter chord line will look something like this, and your quarter chord angle will be this angle. Quarter chord sweep angle. You may want to ask that where are these type of wings mostly used? These type of wings are only used in the cases where you are dealing with supersonic flights. I shouldn't say only, but mostly used. So this sweep angle is going to be a very critical parameter when it comes to supersonic flights. And sweep angle itself is going to be, so lambda is sweep angle, just to emphasize this. The sweep angle itself can cause major changes to your wing characteristics, like the maximum lift, the stall conditions, and also it will change the compressibility effects of the wing, which hasn't been the topic of the discussion in our course. Let's go back to the rectangular wing. Let's try to come up with some definitions. We have already talked about the chord length as well as the span. Okay. The wing area, this is capital S. So here, if you see this as a span, is going to be a small s. Wing area for a rectangular wing is defined as your span multiplied by the chord. But what will happen if you don't have a rectangular wing? What chord value do we have to use? In that case, your wing area is going to be B multiplied by the average value of the chord. You essentially have to take the average value of all of these lengths, and your wing area can be calculated using this. A very important parameter in wing design is the aspect ratio. Aspect ratio is very, very important in determining the aerodynamic characteristics. As well as the structural characteristics of the wing. Of course, the structural characteristics, we're going to see how aspect ratio is going to be very important there. But how do we find this aspect ratio? Aspect ratio on a rectangular wing is going to be this length, B, divided by your chord length. So this is essentially a measure of how wide your wing is. What will happen to this aspect ratio definition if your chord length is changing? If you don't have a constant chord length, you can use the span area for non-rectangular wing. So non-rectangular wings can use the span area, but for rectangular wing we don't need to use the span area. What you're going to see in the real world is that higher aspect ratios are like the aspect ratio of 35, which is a very high aspect ratio, are mostly used in gliders. And then you decrease the aspect ratio a little bit, as lower aspect ratios are like around 10, 8, or 15, 20, something like those values are mostly used in commercial airliners. And when you want to a really low aspect ratio, like the aspect ratio of 2, you are dealing with supersonic fighter jets. What is the reason for this? The main reason here is that higher aspect ratio are going to give you a more stable flight. It is going to be a little harder when you have a very high aspect ratio. It is going to be a little harder to roll. And by that I mean there is a little resistance to rolling. Which this essentially means that you are going to have, when you have a wind gust or something like that, your aircraft is not going to be disturbed. There won't be no disturbance to the aircraft. But at the same time, it is going to be require the pilot more energy to roll the aircraft. Of course, in gliders, you need the maximum stability, as much stability as possible. You're going to have higher aspect ratio, but there are other reasons for it. But one of the reasons is the maximum stability. And as you move on, you don't really want, in a fighter jets, you don't really want to have an aircraft that is hard to roll, because you want it to be as maneuverable as possible. Okay. So low aspect ratios, more maneuverable. High aspect ratios, more stability. And this is a choice you have to make whenever you are designing an aircraft. Do you want it to be more stable, or do you want it to be more maneuverable? Of course, depending on the location, depending on the place you are looking at, sometimes you want to have a more maneuverable aircraft at the cost of stability. That's why fighter jets usually require more practice, more proficiency in flight, and you have your best pilots flying the fighter jets because they need to be able to command their aircraft, because it's going to be harder to command the aircraft. Okay. One thing that I think I forgot to mention here is the taper ratio. So these tapered wings, as I said, they have different chord lengths. So for this type of wings, we define a taper ratio that's tip chord to the root chord divided by the root chord. For a rectangular wing, your taper ratio lambda is 1. For a delta wing, your taper ratio, because of this, is going to be 0. So your taper ratio changes from 0 to 1 depending on the type of the wing. There is another parameter that we need to become familiar with, and that is the mean aerodynamic chord. If you were to do a little bit of fluid mechanics, mean aerodynamic chord, or MAC, would show up in your studies. Mean aerodynamic chord can be calculated using this formula: 1 divided by the span area integral of negative half b to positive half b. I'm going to explain this in a bit. Cy, the changes of chord in the y direction, squared dy. We can actually find the moment of an aircraft wing using this mean aerodynamic chord, for example. This is just an example. Using the moment coefficient q infinity s multiplied by your mean aerodynamic chord. Let's have a top view look at your wings. Let's say this is your fuselage and these are your wings. Here what we usually have, and I'm pretty sure you already know about this because we have done this, is that this is the y-axis where y is equal to 0. We go to positive b over 2 and negative b over 2, which makes your span to be b. There is another important part of the wing design and aircraft design in general. After choosing the appropriate wing, so far we have been talking about choosing the appropriate wing. Right? Do you want to have a rectangular wing, a tapered wing, whatever? The next step is where to put that wing on the fuselage. Let's have a front view of an airplane. So this is your fuselage. And again, if you have a side view, this is going to be your fuselage, your wings, your tail, or whatever. You're looking at this from this point of view. So this is a front view. You want to have a front view to the wing. Where you put your wing is very important. We actually gave, for those of you who didn't have the chance to go over the lecture, we actually had a bonus pointer in this. I told the students in class to investigate different characteristics of this wing location. Which one is going to produce more lift, which one is going to be producing more drag, or why do we choose these? of wing locations, right? But in general, there are four main type of locations. You want to have mid-wing. Wings are going to be located in the middle of the fuselage. You want to have high wings. Wings are going to be connected to the fuselage, but are going to be placed on top of the fuselage. And you also are going to have low wings. I could have used different colors here. Let me actually use. So, mid-wing with yellow, low wing with green. They don't have to be all of them presented at the same time. They can be though. You can have a plane that has all of these together. And there is another type of wing which is called the parasol. That wings are detached from your fuselage. They're connected to your fuselage through wings and placed above the fuselage. This is called the parasol. So if you submit a presentation, a 4 or 5 page presentation to me, it doesn't have to be recorded or anything, just submit a PowerPoint on these type of wings and where they are used, what type of design they can handle, all of those things. You can you will get a bonus point if you submit this, and there's no deadline to this bonus point. You can submit them anytime you want. Okay, but you may ask yourself, why do we always have the wings located in this plane? Let me do a mid-wing here. So the wings always are making 0 degrees with this plane. And to answer your question, I should say that is not always the case. That is actually not the case for a lot of time. We can have angled wings. We can have this type of angle. We can also have this type of angle. So with the XY plane, in general, this is called the XY plane. If this is your Z direction, the angle they make with the XY plane is called the dihedral angle in general. This dihedral angle can be positive, like this, or can be negative. I know we use gamma for circulation as well, but we use gamma for a lot of things in this course, so just make sure not to confuse the two gammas. The positive dihedral angle and negative dihedral angle, this type of wing is called anhedral. When you have a negative dihedral angle, and this type of wing is called dihedral. So we also have these type of designs, but the question is, why do we have these designs? It is possible to design anything, but its use is going to be very important. The main effect of these dihedral and anhedral angles is their effect on the stability of the aircraft. Okay, stability of the aircraft. What does this mean? How do they affect the lateral stability of the aircraft? You may actually want to ask, what is the lateral stability? The lateral stability is the tendency of an aircraft to return to the original trim level. and around the x-axis. So we are talking about roll, let's call it roll stability. Stability. Yeah. So what does this mean is that let's have a wing with a dihedral angle. The idea is that if your aircraft rolls due to a wind gust or something, so its second position is gonna look like this. Having an angle is going to change how your aircraft is going to respond to the type of wind gust that is going to cause this type of movement, the rolling movement. And in case there were some people who knew in class when I asked this, but we have three main types of movement when it comes to aircraft. Aircrafts can pitch, which is the angle of attack. And this is, let's say this is your aircraft. Aircraft can roll, meaning that if they are located in this position, they can roll around this axis, and the new position, your wing will be located in a new position. And they can also yaw, which is your fuselage rotating on this plane. So this angle is only going to affect this type, the roll stability or lateral stability, this anhedral angle. But how would it affect it? When you have a positive dihedral angle, and because of a wind gust, your aircraft rolls in this direction, what is going to happen is you are going to have more lift on this wing compared to this new wing, which means that you are going to have something called a restoring moment. So this restoring moment is going to cause your aircraft to go back to its original trim level. So a dihedral angle is going to do this, but an anhedral wing is going to be the other way around. Dihedral angles, because of this stability concerns, dihedral angles are mostly used in commercial airliners. By anhedral wings, or let's use dihedral wings. By anhedral wings are mostly used in military aircrafts. And this is usually due to the stability concerns that you have. The anhedral angle for commercial aircraft is usually not that big, but it is there, and because of a high aspect ratio, its effects are actually important. Okay, so we have talked so far. We have talked about the type of the wing you can use, the location of the wing, the angle of the wing when it comes to the XY plane, and there is only one more thing that we haven't talked about, that we want to talk about in this class, and that is whether you can twist your wing. What does this mean? Very simply, let's say this is your wing. What I'm asking is that can you apply, I mean, it doesn't really happen in the real world, can you apply torque to twist your wing a little bit? And the answer to that is yes. Let's have a side view look to a wing that is twisted. This essentially means that your tip airfoil is going to look like this, whereas your root airfoil is going to look like this. And this is still, keep in mind that this is still on one wing. Your tip, your root. So these are actually connected to each other, right? This is still one wing. So we can have a twist. In general, we have two types of twist. We have a geometric twist that based on the twist, essentially based on which one of these are alpha of t. Let's call angle of twist alpha of t. Which one of these is on top, right? We can have this position, or we can have your tip look like this and your chord, your root look like this, which means that your tip is going to have a higher angle. Based on this different location, we can have two different flow patterns on your wings. We can have wash out or wash in, and this generally talks about the type of the flow pattern. You're going to have wash out, which is a more common thing when the angle of attack at the tip is lower than the angle of attack at the root, which is the more common one. And this one is when your angle of attack at the tip is larger than angle of attack at the root. This is a more common thing that happens, which is the first case. And we will talk about the flow patterns, the different flow patterns on this washout and wash in a minute, after talking about the aerodynamic twist. So there is another type of twist which I think I didn't mention in class when we were talking about this originally. Aerodynamic twist talks about the fact that your airfoil shape may vary from the root to the chord. What does this mean? This essentially means that at your root you can get a NACA 2412. At your tip you can get a different NACA. Let's say NACA whatever 2515. Just a random number, right? So you can have different NACAs, different airfoils at the tip and the root. That will also change the flow pattern of the wing. Well, how would the flow pattern change? Let's go back to the geometric twist. And how would the flow pattern change when you have a geometric twist at the tip? If you look at it more closely, let's say, let's redo the plus here. Again, this is a side view. Let's say this is your tip, and then you are increasing the angle as you go to the roots. The main effect on the flow pattern the geometric twist has is to increase or decrease the angle of attack as you go from tip or root. Let's say this is your original angle of attack, right? Your angle of attack at the tip is going to be equal to alpha 1 here, like, or alpha of tip. Okay. But the angle of attack at the root is going to be a little higher, alpha root. So for this design, alpha root is going to be larger than alpha tip. What is going to happen when this is the case? To answer this question, you have to go back to the CL versus alpha plot. Let's say you have symmetric airfoils, meaning that your alpha at zero lift is 0. Your tip is located at here, right? A low angle of attack, which is generating this much lift. But your root is located here, right? Because it is higher. So it is generating more lift. So you're going to have more lift at the root. But also, as you increase the angle of attack more and more, your root is going to reach the stall condition faster. Stall condition faster. Which essentially means in this type of wing design, you will have a case where you will have a stalled root, but not a stalled tip. So the stalling on the wing is going to start from the root and then move on to the tip as you increase the angle of attack. And this is going to cause the washout phenomena. Why is this important? This is very important mainly because you are going to have your ailerons, which are your roll controllers, are going to stall later. What does this mean? It means more stability for the aircraft. This is why this is a more common type of design. But on the other hand, in the other case, when you have wash-in, your root is going to stall later. Which is going to result in a higher maneuverability. Okay. A washout design is usually combined with something called a forward sweep. So you have your regular backward sweep and also your forward sweep. What does this forward sweep mean? If you have, this is a top view of an aircraft. Your regular planes look like this. Your wings are swept towards the back of the plane. But there are some very special cases in which you are going to have forward sweep. Your wings are going to be swept forward towards the nose of the aircraft. What is the benefit of this is that you are going to have reduced drag and more maneuverability. So more maneuverability, reduced drag. But you may want to ask, why is this not design used at all? Because this design, it is very, very hard to control. And by that I mean it is very maneuverable, so it is going to be very responsive to your commands. So controlling is not that hard from that perspective. But it is not a stable flight. So you always have to be mindful of all of the wind gusts and all of those things. There are two very famous aircraft that have used this type of design. One is the bomber the German used, called the Junker U-287 during World War II, and the other one is the X-29, which was built by Americans in the 1984. It was built by NASA specifically. At this point of the lecture, please go to, let me give you the page number, page 15 of the lecture notes. There is a video uploaded there, page 15. There's a video uploaded there on the for the X-29 aircraft. What I'm gonna do is that I'm gonna upload my PowerPoint presentation, a PDF, so you can play that video if you were interested to watch. And we actually played that video in class. All of this brings us to the most important topic of the finite wings. That is going to be our main focus for the rest of this lecture, and that is called the downwash phenomena. We actually covered most of this downwash phenomena in the next lecture after the lecture we had on March 31st. But I think it is not a bad idea. We did a very small introduction to this when we were talking about the wings in general in the lecture on March 31st. So I'm gonna do the same just to make sure you haven't missed anything. Okay. The main thing you need to address here is that what is going to happen when we move from a two-dimensional wing, which essentially is an infinite wing, to a three-dimensional wing, which is a finite wing. What is going to happen to the flow pattern? Let's take a look at this front view of the wing. So your air is coming in this direction, and you have a high pressure compared to low pressure throughout high pressure region on the lower surface and low pressure region on the upper surface. This, as we already know, is the main driving factor or main generator of the lift. When we were talking about an infinite wing, which is going to continue throughout this page, we wouldn't have any problems because you will have this pressure distributions throughout the wing. You will have the same pressure here as here, and here as here anywhere, right? But when you are talking about the finite wing, what is going to happen here is that at this tip, you have a very high pressure region and a very low pressure region at this tip. Again, high pressure, low pressure region. What is going to happen when you have, let's say in a pipe, you have a high pressure region here and low pressure region here? You will get fluid flow from a high pressure to low pressure. So the same thing is going to happen to the tip. You will have flow moving from this high pressure region to the low pressure region, and this is going to happen on the other side as well. This phenomenon is called the downwash. So, what is going to happen because of the downwash is actually very interesting. You have pressure at the tip on the lower, let's magnify this tip, let me magnify it here. Let's say this is a tip. Your pressure on here and here has to be equal, because whatever pressure, higher pressure you had has already leaked to the top. Okay, what does this mean? It means that delta P of the tip is 0. And we said delta P, this pressure difference, is the main generator of lift. What does this mean for the lift at the tip? This essentially means that lift at the tip is going to be 0, right? So you can safely conclude from here is that as you go further in towards the fuselage, these pressure leakages are going to become smaller and smaller because the flow has to move a longer path, right? So if you want to draw the pressure distribution, or the lift distribution, your lift is going to go from 0 to a maximum value on top. Let's say this is the distribution of lift per unit span on the fuselage, and then it will go back to a minimum value on the other tip. And this is also means that we are going to lose the rest of the lift. If it was an infinite wing, your lift distribution should have looked like this, right? So we have lost these parts. The lost parts are going to contribute. I mean, because of this loss, we are going to have something called an induced drag, which I'm pretty sure you have already watched those lectures, and you're already very familiar with the concept of induced drag. So I guess that's it for today's lecture. See you all on Monday. Let me know if you have any questions for the exam. Don't forget your exam is on Monday, April 19th. Have a good day.